Okay, so can you hear me? Okay, so thank you very much for the organizers for inviting me. And this is an excellent chance to talk about the kind of work I'm doing at the moment. And I have to say sorry because I've seen the recent subjects of the conference, and I actually, since it's a quantum device, I centered quantum devices. But anyway, you guys are going to see a few models related principally to sonic models, and you're going to see some connections to what here at the. Okay, so I'm going to talk about a recent model that we developed and how to implement it using some superconducting devices. And before I can go on, I cannot talk about this new model of quantum walk without speaking about discrete time quantum walk, some previous ideas on quantum walks, and continuous quantum walk as well. And depending on time, I will show you the implementation, some proposal for implementation of those quantum walks. Okay, so what is a quantum walk? So the first idea, at least for me, as far as I know, the first paper that mentions any relation that coined the word quantum random walk was this paper, which is by Luis Davidovich, Haronov, Yakira Haronov, and Zaguri, and is from 1993. And although this was the first paper, there is a mention that some people relate that in the previous paper by something around 83, the very popular paper by Feynman, where he discussed the first paper, he discussed quantum computation. Some people interpret that actually he has some addressing to this sort of continuous quantum walk. But anyway, this was the first paper that mentioned in the title even the quantum random walks. But the idea that I'm going to present is a little bit more modern, the modern version. So what people call in terms of discrete quantum walks and continuous quantum walk. So everybody knows what is a random walk, but the quantum walk is similar to that one, at least the discrete quantum walk. And the only point is, which is different, is that the coin is can live in a superposition state. One dimension for the moment. One dimension. Yes. 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 Yeah. I'm going to generalize this, but square lattice or on the sort of. We can have this, for example. Yes. Okay. I don't know that one. Yes. Okay, so that's mostly I'm going to talk about one-dimensional quantum walk, but then I'm going to show you we need to go to larger dimensional systems. So let's suppose that I have a coin in a superposition of heads and tails. Okay, so that depending on usually the random walk in a line, so we have a discrete lattice, and depending on the heads or tails, the walker gives a step to the left or to the right. Okay, so now if we have a coin that lives in a superposition, don't measure the coin at any moment. Okay, so it lives in a superposition. What we end up is that the walker actually has a superposition and forms an entangled state. This is very important. The coin going to the left and to the right simultaneously. So that's quite important. We cannot look at the coin at any time step. Okay, so the difference is here. So for example, this is a way to implement random walk. If for example, I put some pins in a board, and this is so-called Alton board. And then I repeat this experiment many times with many balls. What we end up is with a normal distribution at the end. If we have many sites, we see a sort of a Gaussian shape for the distribution. Okay, so depending on the time steps, meaning the first time step, second, third, and so on, the distribution is going to be to disperse. A dispersive regime, which is diffusive mechanism, and which is depicted here. So if I look to the dispersion, this is the classical one, it goes with the square root of t. This is quite important for quantum, as I'm going to talk later. But if you have the same situation, but with the same walker, but with a coin that can live in is with something which is completely different. And the profile is very characteristic of a quantum and interference, interference of probability profile. And we end up with accumulation of a density for the particle to be either here or here. Okay? So the dispersion in this situation, diffusive mechanism. So it goes, instead of going with the square root of t, it goes with linearly with time. Okay, this is very important. So this is very easy to implement in principle in one dimensional. Okay, so let's suppose that I have a collection of mirrors here, and I send one single, and I reflect or transmit this photon. So what we end up is with constructive and destructive interference in a way that this profile will be formed. Okay, so this is actually some of some experiments that were done at this by Christine Cyberhorn a few years ago. Okay, so let's now go into details what the discrete time quantum walk means. The main components that we need is a walker, which whose dynamics occur in this Hilbert space. Here is spanned by the sites. So let's suppose initially this is a one-dimensional quantum walk. And also we need a coin with at least a two-dimensional Hilbert space. Of course, we need two states to decide whether we go or to the right. And we need also a coin operator that generates the superposition of states. This is very important. Otherwise, we have the similar classical walk and random walk that we had at the beginning. And we also need a shift operator. The shift operator is the one that is going to tell the walker that it must go to the right or to the left, depending on the state of the coin. Okay? For example, infinite, for example. Yes, and then we have to include the boundary conditions for that. Usually, usually we have in the experiments what we have is a reflection. Yes, so usually this is so we have to take into account this kind of problem. So the unitary evolution is simply a sequential operation of the coin and the shift operator that we have to apply in a sequence like that. Okay, so in this process many times. So by the number of time steps here, we have the final wave function describing the walker plus coin state. But there's another one. Okay, so this is very, in principle, the discrete quantum walk is simple to describe in terms of one dimension, but it's quite very difficult to implement in 2 dimensions and 3 dimensions and so on. But let's go to the continuous quantum walk. Continuous quantum walk is very different from that one. What I suppose is only the coherence. So let's suppose that I have a Hamiltonian, and this Hamiltonian is formed by those terms. I have only interaction with the first neighbor, and don't have any other interactions. And also I have some terms that count for the self-energy for this Hamiltonian. Okay, so if we transpose and write this in terms of bosonic operator, what we end up is a Hamiltonian. Yeah, sure. Yes. So, but we have to normalize somehow. Yeah. We have to renormalize. Yeah. No, that's fine. Okay. So what we end up is with a Hamiltonian, which is very similar to the Bose-Hubbard Hamiltonian interactions, and this is everybody's familiar about this kind of Hamiltonian. Whenever I have a system that I can implement, and then we're going to see in a similar way, we're going to see a profile for this quantum walk. Bosonic, that's right. Okay, so for example, this is a very simple way to implement something that we did last year. So it's a way to implement this quantum walk in terms of an array of electromechanical resonators. So those electromechanical resonators, they actually, you know, like a few years, something like less than 10 years now, we have very large development of this area. So some experimentalists, they reached the situation where we can cool down those resonators right to the ground state. K capital is millikelvins, okay? Okay. We are going to describe those resonators quantum mechanically. That means that we have this quantum energy larger than any thermal energy, thermal fluctuation. So in a sense that if we reach the temperature around millikelvins, we must have frequencies around gigahertz. So those resonators are real, actual. I don't know whether I don't have a, anyway, this is, no, around nanometers, okay, a few nanometers. So this is actually all related, okay? So in order to check whether the frequency, the size and the frequency, they are related, we cannot uncouple this. Okay. So this is actually some experiment that is being done, you know, in the community with the experimentalists have been implementing this. But let's suppose an extension of this kind of experiment where I have just one resonator. Instead of that, I have many resonators that are capacitively coupled to each other. So it's a very weak interaction between them. And if we describe the interaction, okay, and if I have a frequency which is around gigahertz, I can describe this in terms of this displacement operator. This operator is only related to the I have it somewhere here. So this is it. Okay. So if I have one resonator, and the average distance, it's going to be taken into account the average distance between this resonator and the next one. Okay. So then, if we expand this around this average displacement, what we end up is with the interaction Hamiltonian interaction potential being written in terms of this term. So what is this guy here? This guy is just something which is fluctuating with time at gigahertz, okay? But the other term is fluctuating. What is important is not the way it's fluctuating around zero, because this guy is fluctuating around zero. So either it oscillates to the left, to the right, so the average is zero. But this one is actually this the size of this fluctuation. Okay, so this is more important than this guy, but this is important to what we're going to describe. Okay, so let's suppose, so if we have this, when we recollect those terms and write down the quantized Hamiltonian, what we end up is exactly with the Hamiltonian that I showed you before, which is the Bose-Hubbard Hamiltonian without interactions. Okay, and all those terms, all the collected terms are written here. But the point is, I didn't tell you about, because I want to describe something else, not just the continuous quantum walk. What I want to describe is also localization. I assume that I have a random distribution of frequencies for each one of those resonators. Okay? So if I assume this is randomly distributed over an average frequency minus delta and n plus delta, I can call this delta as a disorder intensity, and which is very small compared to the, in terms of experimental numbers, it's very small compared to the average frequency as well. And also is small, doesn't need, even the interaction between those resonators, it doesn't need to be large as well. Okay. Yeah. This one or this? This is the 0 point, this is just an energy, this is 0 point fluctuation. Okay? Yeah. So this is a standard thing indeed, that we always quantify in terms of the mass and frequency for the resonator. Okay, so just one point. So everybody knows what Lenderson localization is. So this is actually related to a wave-like phenomena. And whenever we have, if we compare, so let's suppose that I have a collection of scatters here, and I have an incident plane wave. I decompose this. And I have a few important numbers here. The size of the system, which is described by capital L. The mean free path, so the average distance between sectors, and also the wavelength for this incident wave. So whenever, for example, I go, so let's suppose that I increase the size of the medium, and if it's larger than what is so-called localization length, then we have a localization of this distribution. And also, similarly, the same kind of phenomenon occurs if we increase, for example, this strength of disorder. In one-dimensional system, it always happens, but we're not going to describe this in details, okay? But there are, so this, depending on the size of the system and the strength of the disorder, we have a transition between those many possibilities of inside the system, okay? So let's look at the results, okay? This is just to describe what we have, okay? So if we consider, for example, in the same collection of resonators, I assume that I have just one single excitation, because I just want to describe this. So if I have one single excitation in the BOSE-HUBBARD Hamiltonian, without interactions, what I end up is with the Anderson Hamiltonian, and remembering that I have this frequency which is randomly distributed as well, then we end up with something which is similar to this, okay? So what I'm plotting here. So this is actually the density system. So I have one resonator, so I have a collection of 51 resonators of those, weak coupled to each other, and I put a single excitation. So this is very easy. I just put a capacitor and I put some excitation to this capacitor, and somehow this allows that I have one single excitation in a specific situation. And then I see the evolution of this excitation over the chain, okay? So this is actually some interference profile, as we can see here in T1, T2. So this is a very characteristic of the quantum walk profile that we've seen before, okay? Moreover, if I allow that the system has somehow some disorder, I allow some very small disorder in terms of the resonator frequency. Instead of this profile, what I would see is a localized profile as expected. And this is interesting because what we see here is exactly this, but instead of looking at the density, I'm plotting the entanglement, meaning that not only the particles are localized, but also the entanglement is localized. T, and again the sites, and what's being plotted here is the concurrence between the central resonator and the neighboring sites. Yeah, yes, yeah, okay. Yeah. Single particle. Yeah, but I'm talking about it's not entanglement between particles. Is entanglement, what we call entanglement between modes. So this is entanglement between one site and the other one, and so on. Okay? So usually, so if we had, for example, in a situation, I don't have the figure here, unfortunately, but if we had this in that situation without localization, what I would see is exactly the same thing here. And this is interesting because this behavior is very robust to temperature, to any extra effect. So here we included in a simulation the effect of a thermal reservoir. One thermal reservoir to each one of those resonators independently, because this comes from quantum current description. And what we see is that even with some a very large time evolution, the evolution time, what we see is that the entanglement is still robust, okay? So what happens after that is that thermal effects are taking over the system as expected. No, no, no. No, we have studied as well the multipartite entanglement in terms of the, but there is a problem with this in terms of. Hmm. Yes, we do. That's true. Yeah. Okay, we have this. But also, and whenever we don't have entanglement, bipartite entanglement, somehow we have some conservation of entanglement over the lattice in a way that, for example, if we take part of the system and plot the entropy, then the entropy is larger. Okay, so this is an indication that multipartite entanglement is there. But this, we cannot use this, for example, I can only use this when the system is pure. I cannot use in the situation where we, okay? But anyway, this is just to show you that we have an easy implementation, a simple implementation of this quantum walk, continuous quantum walking, even in a system that is chain of mechanical resonators. Yeah, yeah. This is just, I mean, put the. Exactly. Yeah, we described that. No, it's not quadrature. We don't need that because to each one of those, we could have a single qubit. And we probe the resonator, which is capacitively coupled to this qubit, and then we probe the qubit. We don't need this. What we propose in the paper that we just have one resonator, and we ramp up the frequency of this resonator, the qubit, sorry. And this qubit is coupled to all of the resonators. But since normally is far from resonance of any of those resonators, it doesn't, it doesn't suffer any. So when I ramp up the frequency, the qubit will interact strongly with the resonator, which it is resonant in frequency. Okay. No, it is. Yeah, we actually in terms of circuits we measure also we measure things which are related not to quadrature but C, A. We measure the average of A, not A dagger A. We don't. This is called linear detection processes. So they can do even better than what we can do in quantum objects. No, 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 no. No, no, this is just a theoretical proposal. Yeah, okay. Well, to measure that, we would have to reconstruct the state and then to calculate that. Usually as, yeah, that's right. Yeah, okay. Okay, so why did I describe these two models? So now we have to, so you could ask, so, okay, and what is the point of this quantum walk? So what happens when what is a quantum walk useful for? This is the question, okay? So this is important because whenever, for example, so let's suppose I have a problem, a simple task, and I have a collection the similar way. I have one-dimensional collection of sites, and I mark one of those sites. What? Where? Where? Oh, no. No. Sorry. Okay. Okay. Yeah. No, it's work, really. It's the paper. A paper that addressed the problem. Publication, that's right. Yeah. Okay. So let's suppose that I have somehow I have a situation that I can perform a quantum walk over a chain. Okay. And I mark one of those chain sites. I can use this quantum walk dynamics to perform a search algorithm. So this is well known by the computation scientists, and they actually have a relation to this to the complexity of the search algorithm and this quantum walk, the random walking dimensional and d-dimensional, whatever. Okay, so this is a depiction of the similar thing that we have in terms of quantum walk. Okay, either for the continuous quantum walk or for the discrete quantum walk, in terms of many proposed algorithms to perform the search algorithm in terms of this quantum walk. So the first one to propose this was this paper back in 2003. Okay, so before I describe, I have to say, in one-dimensional, no quantum search algorithms in terms of quantum walk can do any better than any classical search algorithm. So we have to go to a higher dimension. So when we have a two-dimensional system, things start to get different here. So for two-dimensional, for example, the first algorithm, the first search algorithm based on quantum walk and based on the discrete quantum walk showed this scaling. This scaling means the worst situation that we have. So of course, for example, one could be very lucky and with a single step find the marked site. But usually, if you are unlucky like me, you would take, you have to walk over the full lattice to find the site, market site. So that's the worst situation. This is the capital O notation. So in the classical situation, it would take something which is linearly dependent on n log n, and where n is the number of sites. But what we see here is something which is better than that. So this is because we showed that the dispersion goes to the quantum walk, the dispersion goes linearly with t, while the classical walk, it was diffusive, so it was going with the square root of t. Now is the other way around, so this scaling is actually some speed up that we have related to quantum algorithms. But the point is, if you compare the continuous quantum walk, for example, so the continuous quantum walk that I just showed to you, instead of going with the square root of n, it goes linearly with n as well, so it cannot do any better than the classical walk in two dimensions. Ibanez, it's called Ibanez, yeah, yeah, okay, and yes. But if you see that I can only have something which is better than the classical one if I increase the dimension to dimension 4 for the continuous quantum walk. So this is quite important, meaning that even though this continuous quantum walk in some fashion easier, very difficult to use this for quantum walk, for a search algorithm, quantum search algorithm, because it asks a dimension which is very large, and this makes this very difficult to implement. Experimentally. No, it's difficult. It's really difficult, okay? Even in terms of optical systems. So optical systems, they can do one dimension, but two dimension is hard. So what they do, what they do is instead of using two dimension, they use a two-particle quantum walk, which somehow simulates what is happening if the particles are not dependent, okay? So they include some correlation by hand, so they can do that. So this is important because somehow so all those guys here which are not marked, they are discrete quantum walk as well, and we see that this scaling, nice scaling going with the square root of n is going on here. But the continuous one, I can only improve the scaling if I add another coin. But this is interesting. Adding another coin, meaning that I treat the system like a spinner. And therefore, the dynamics of the system is not described by the Schrödinger equation anymore, but is described by the Dirac equation. And one quantum coin. The coin here, because this is the continuous, doesn't need a coin. The continuous doesn't need a coin, okay? We have the evolution of the system. So naturally, the evolution describes this profile characteristic of the quantum walk, okay? But this is interesting, and therefore this system is also very useful, not only for performing this kind of quantum walk or quantum search, but also for simulating quantum relativistic effects. And this is a very interesting thing that we have. Yeah, exactly like that. So it's very useful for simulating gauge theories. Yes, that's right. Yeah. Okay. So it is amazing. This is really amazing that we have the same thing describing the necessary elements for describing a specific quantum walk, and this is exactly the same number of elements for describing those theories. So this is something that I believe, and not only me, but some other people believe there is a very important connection there, in terms of very deep physical meaning. Okay. But then I'm going to describe another model, which is the staggered quantum walk, and I want now to show you that and try to convince you that this quantum walk is actually, this model is actually nice, because it somehow it brings some performance which is similar to discrete quantum walk, but also is easy to implement similarly to the continuous quantum walk. So I did not analyze this complexity, but this is present in this paper by my collaborator, Renato Portugal, and which was published this year. So they proposed a quantum algorithm in 2 dimensions that shows this scaling as well. Okay, so what is the staggered quantum walk? So instead of working, this is inside the family of coinless quantum walk, meaning that I don't use a coin, but it's not continuous as well. Because instead of considering a unitary evolution, I have a collection of staggered unitary evolutions. Okay? So the evolution operator is just product of local operator, 2 or more independent graph tessellation. So one tessellation in 1 dimension is shown here. So I connect this. This is, you guys are probably familiar with that in terms of some. The end of my chain, they have to be isolated like that. Okay, so I have to perform this dynamics. So otherwise, this is not important at all. So introduced a new model, which is so staggered quantum walk Hamiltonians. So the computer scientists, they don't use Hamiltonians, they use unitaries. But the problem is that this staggered quantum walk was proposed in terms of Hermitian unitaries. Okay, so whenever we have unitaries that are Hermitian, of course you cannot use Hamiltonians. So in terms of the evolution operator, but we have extended that. Extending that, we end up with the following description. So the unitary that we apply is like that. So I have a Hamiltonian evolution for each tessellation, and this tessellation means, if I translate this in terms of bosonic operators, means that I have somehow to connect in a way these 2 sites, neighboring sites here, but I have to turn off the interaction between these 2 sites here. Okay, so therefore I can use in a similar way a chain, okay, of sites, some models, some bosonic models, but I have to control the interaction in a way that I have to I have interaction only with the second and so on. Okay? All right. So, okay, so this was proposed in this paper. So this is again, as you can see, the similar BOSE-HUBBARD Hamiltonian without interactions, but for the sites that I'm connecting here. All right? So we can actually extend this to any dimensions. This is useful because we want to describe somehow the search algorithm, and we can extend this to 2-dimension and 3-dimension, and we for any what is called triangle-free tessellations. Tessellation is I have a graph, okay? Somehow I have a graph, and I try to cover this graph somehow with specific connections. Those connections are the tessellations. So the tessellations, I have to patch every part of the graph in an optimal way. Okay, so there are many ways to do that, but we can do the way we propose is a triangle free. So any kind of geometry that is triangle free, we can cope this with the algorithm. Okay. Okay. So this, all right. So this is in a general picture. What is this staggered quantum walk with Hamiltonian? So the blue one is the whole class of this proposed staggered quantum walk with Hamiltonians, and inside of this class is the previously proposed simple staggered quantum walk, and mentioned it covers a previous model of coinless quantum walk that has a few problems on it, okay, but people understood that afterwards. This guy proposed it a few years ago, but we also covered this problem. We cover as well some coined models, meaning that this discrete quantum walk with a specific coins here. I'm not going to describe this, but I have ending results which are completely different depending on the coin, on the operator that I use to generate the superposition of the coin. Okay, so H is for Hadamard, G is for Grover, which is the best one, and F is for Fourier coins. It's just application that generates the Fourier transform over the basis of the coin, just that. While the Grover generates a superposition. But this is amazing. The initial state, this is an evolution which is very dependent on the initial state. So if we choose a specific coin, which is, for example, the Grover, is the one that we get the best scaling. Okay, so this is what we have. All right, so now I really to implementation, and I will try to move faster. Otherwise, I will go over my time. Okay, so for that we need to describe a few circuit elements. So the good thing on using superconducting circuits is that we have a strong coupling between qubits. For example, if we generate implement in terms of qubit, I'm going to show you that we need one of those, not only one, but a few qubits, and we would have fast gates. We also have an easy access through electric signals over these guys. And in principle, it's easy to fabricate compared to the other technologies that we have around. But also, there is a problem here, which is the strong coupling with the environment, meaning that I have a rapid decoherence. By the way, decoherence, if I had that coin, that initial coin for the discrete quantum walk, if I had a coin with decoherence, so this guy would behave exactly as a classical random walk. Okay, so I don't have any advances in using that. Okay, so for the qubits, we have two options, either using what is so-called the charged qubit or using the flux qubit. We use the charged qubit, which is better for our implementation. So we have Josephson junction, which is separating two superconducting areas. One is so-called the Cooper pair island, and we have a Josephson tunneling between these two sites. If I go in the so-called charge degeneracy point, which is around here, what I see is a splitting of two bands, and these two bands I can encode what is called the bit 0 and bit 1. This is the qubit. Nanometers. I don't know exactly how but it's nanometers. Okay. But if we, instead of using just one single junction, we use two junctions, this is better because we can control the way this guy, splits or is described without splitting, just by electromagnetic pulses over this device. Okay, so this is the way that we're going to use. Another element, we have to connect this guy to what is called the microwave resonators. Microwave resonators, this is a cavity for microwave radiation. And we also have some experiments. Sorry, it's cutting here, but we have some experiment going on, and many experiments actually which are already connected those qubits to these microwave resonators. So just to show you, for example, here I have one single resonator, one mode resonator connected to one single Josephson junction, a device, a single squid, in this case. And here I have many modes connected to this also to different qubits. Okay, so the way that we propose, and I tell you why we need that. We need to, instead of connecting these these microwave resonators by just capacitively, I have somehow in between these resonators. Therefore, I need some element that I have access, an external access, in a way to turn off and turn on the interaction. Okay. And large coupling between this resonator. Therefore, the only way to achieve this guide. So the way to calculate this, we have to go and describe this in terms of lumped circuit element, calculate the Lagrangian, and to derive this. At the end, what we end up with the Hamiltonian, which is Hamiltonian with interaction, but with an extra term, which nearest neighbors. Okay. If I externally, I have a profile of pulses which is exactly like that. So to simplify, we suppose, for example, a train of pulses, of spare pulses. Have these guys which are under the yellow arrow. Okay. So one thing important, this is we use accessible parameters. So this is of since the single photon lifetime is large seconds, we have this is plenty of time to do any simulation that we want in terms of this system. Okay. Okay. So this is to summarize what I had before in a way to describe this Hamiltonian. So I don't bother you with these details to the derivation of this. So our Hamiltonian is split in terms of two Hamiltonians for the tessellations, for the different tessellations, and at the end I have a unitary evolution, which is the combination of this Hamiltonian, the unitary evolution for this Hamiltonian 1 and the Hamiltonian 0. And again, I just have to apply this many times in a sequential way. It's just a to control experiment. It's just this is related to the size of the pulse. Yeah. Yes. Okay. So indirectly related. So we relate this. So this is just a parameter here, just to simplify. But this is related to the magnetic pulse due to time that I leave this pulse on. Okay. So now I have to apply this over a sequence of times, and what we end up is with this nice profile for the quantum walk. So here we have some which is not. So for example, if I use the Grover coin, what we end up is exactly with this profile. So instead of having two peaks accumulating at the end, I have just one here. Okay. But if I use the Grover coin, then I have this profile which is nicer here. All right. So just to show you. So this is interesting because. So just to mention why is this important? Because it brings somehow some resemblance with the discrete quantum walk in a way that is useful. If I can implement this in two-dimensional, it's useful for implementing search algorithms, quantum search algorithms. But also is simple in a way to implement, because I can use potential systems that I could use for the continuous quantum walk, but now I have to add extra control over the interactions, then I can implement easily this system, which in the other way would be very difficult to implement. Okay. All right. If we can, for example, let's go for 2 dimensions. This is not done yet, but I mean, we didn't do this in terms of proposal for implementation. But it's very simple. We have just to extend the application of those square pulses in a way that we have the tessellation for each unitary evolution described in this way. Okay. Yes, yes, we can do this. Yes, so this is what we have some problems with this, because they do interact as well. We have interference between resonators that we don't, so we want to turn off. So this is the point. This is the most difficult point that we have for this. Okay. The second one, which is something that I didn't discuss, is to implement the search algorithm. To be able to implement the search algorithm, I have to generate a superposition of the full lattice. Okay. So then, if I implement this, if I'm able to implement the superposition, then it's fine. In this system, in principle, it's very easy to do that. It is easy. If I can implement this with some, at least I have here, you know, like I have interaction implementing one tessellation, and I don't have the other one on, then it's possible. Okay. This is just the conclusion then. The first one is just what I told you. I mean, this is interesting because this staggered quantum walk with Hamiltonians is important in a way that inherits interesting properties from both continuous time and discrete time quantum walks. So there are many things to be developed in this model, so we didn't do yet, we are doing. So one of those is the investigation of the realistic conditions, this we are doing right now, for implementation in 2D, and therefore the implementation of this quantum search algorithm. Okay. And the second one, which I didn't mention, is that quantum walk is universal for quantum computation. So if you have a system that implements quantum walk, you can do any result, any outcome of a quantum computation. And then in a similar way, this we expect that this is universal as well for quantum, or in other way, you can do universal quantum computation. Okay, and that's all.
Okay, there have been many